So this lecture is going to go over the fundamentals of covalent bonding. Um, and so recall a covalent bond is a bond that's resulting from the sharing of electrons between atoms. So this happens when two atoms share a pair of electrons between them. So we can consider, for example, the simplest molecule, H2, made of two hydrogen atoms. And we can think about each hydrogen atom, recall, has an electron configuration of 1s1. So what we're really doing is bringing two s orbitals together, right, and have these s electrons, instead of associated with a single nuclei, be associated with two nuclei. And so pictorially, we can imagine H dot, where that dot is an electron, or we can imagine this is our s orbital. So imagine your s orbital, remember, a spherical orbital, a probability distribution of finding an electron. So if we bring a second hydrogen atoms together, another H dot, and we have, in this case, we have H dot and H dot. Our final product, we're going to represent the bond, the shared pair of electrons, as a solid line. Anytime you see a line connecting atoms, that represents a covalent bond, and it represents two electrons. And so what we're really doing is taking our s orbital and our s orbital and bringing these together to form a new orbital that's a molecular orbital. Instead of residing with a single atom, that now we have a probability distribution that's across both nuclei. So both of these electrons, instead of being in separate s orbitals, are in a new orbital that's a covalent bond that is shared between the nuclei. All right, and when we think about this, I want to take a quick detour and just talk about energy for a second. And let's think about an energy change that we know, and then we'll apply this to our chemical bonds. And so imagine we want to think about boiling water. So how do you boil water? You put a pot of water on the stove and you provide heat. And so showing that in an energy diagram for boiling water, we would have energy on the y-axis, and we'd be starting off with water as a liquid, and we need to go to water as a gas, right? We're turning water as a liquid into a gas. How do we do that? By providing energy. We provide energy. We put it on the stove, we put it over a fire, and that heat helps turn the liquid into a gas. So this change in energy is zero, right? It's zero because our final energy, greater than zero because our final energy state is greater than our initial energy state. So if we think about energy diagram of sodium chloride formation, we said that when we form sodium chloride, the salt, recall, we said that is going to release energy. Energy is coming out. So we have sodium plus chloride forming the salt. This is an exothermic reaction, meaning energy goes out, right? And so we've released energy. So a couple key things to keep in mind. It means that positive energy changes mean that energy is absorbed, and negative energy changes mean that energy is released. Let's think about an energy diagram then for hydrogen, molecular hydrogen. We said, what are we doing? We're taking two 1s orbitals, hydrogen with one electron and hydrogen with one electron, and we're bringing them together. And what I want us to consider is, what is more stable? The hydrogen atom with the electrons in a 1s orbital, or molecular hydrogen, H2? When we think about this, one rationale for understanding which is more stable is just to say H2 must be more stable because it exists. If this was not more stable as a molecule, it would just blow apart and turn into atomic hydrogen. But why is it more stable? Why is it that this covalent bond is more stable than the electrons in a 1s orbital? And in order to think about that, we have to think about, again, what's happening. We have two hydrogens, each with their own 1s electron attracted to it. And the key of this covalent bond, so if we do it visually like this, or like this. The key is that each electron is now shared or attracted to two nuclei, right? Why did we get more stable? Why is energy released when we form that? Because we're forming another force of attraction. Each electron, which was associated with a single atom, is now associated with two nuclei. So we're forming forces of attraction, which is inherently a stable event. So when we think about what are the attractive repulsive forces present in H2, we can start to really analyze it and say, if this is our hydrogen nucleus, 1s orbital, 1s orbital, we see we have repulsive forces between the electrons, repulsive forces between the nuclei, but we have attractive forces from each electron to each nuclei, from each electron to each nuclei. And it's these attractive forces are greater in energy than the repulsive forces, so therefore hydrogen will be a stable molecule. So if we keep this picture in mind, we can then ask ourselves, what happens if we sort of change this distance between nuclei? So, for example, if we have H, where the hydrogens are really far apart, or H, where the hydrogens are very close together, a long bond or a short bond. So what's going to happen to our forces of attraction and repulsion? And that's what this picture from your text is trying to illustrate, where we have energy on the y-axis and distance between the hydrogen atoms on the x-axis. And so what we can see is if the hydrogens are really far apart, we have no bond. These are two atomic hydrogens floating apart. We have no bond. Our energy is zero, right? Because there's no forces of attraction and no forces of repulsion between these. As these molecules start to come closer together, as we start moving this way, an internuclear distance, we start to form a force of attraction, right? The electron from one atom is being attracted to the nucleus of the other. So the formation of a force of attraction is going to release energy. So we have a negative energy, and it's going to go down, down, down as we keep getting closer and closer and closer together until we hit sort of what we call the bottom of this well. So we're going down, 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 and we hit this distance right here. At this point, if we go any closer between the atoms, our energy starts to go up. So what's happening? Why is our energy going up now? It's because these repulsive forces are starting to get really strong. And we can't bring them too close to each other. So if we go up too close together, we get energy above zero, which means the repulsive forces win, and we're essentially blowing apart our molecule again. So if we bring these too close to each other, the molecule is going to repel each other and the atoms will go away. And so what we're really seeing on this diagram is initially the atoms are far apart. As they come closer together, if we're really close, repulsion forces win. If we're really far, there's no force of attraction. At the lowest point in the diagram, at the lowest energy, we have what we call the bond distance. This is the bond length or bond distance between the two atoms. This is an average distance, and this is what minimizes the energy for each molecule. All right, and this amount of energy between the bottom of our well and zero is what's known as the bond energy. How much energy it takes to break the bond. All right. So that's our short introduction into covalent bonds. We're going to be talking a lot more about them. A quick note on metallic bonds. A metallic bond is when, and this happens when you have a metal substance and only a metal, where electrons, instead of being shared between two atoms, they're shared between a whole bunch of metal atoms. So instead of having electrons shared between two nuclei, these electrons are sort of delocalized over the surface of all of these metal atoms. And so we often think about this being as a sea of mobile electrons that can move freely. One of the consequences of this, if electrons can move freely, like in this copper wire, it's really good at conducting electricity, because what is electricity? It's just the movement of electrons. Thank you.